Good day to you, and welcome to Fascinating. I'm your host, Rick, from planet Vulcan. My ongoing mission on planet Earth to search for signs of intelligence and to encourage its spread. During the first 3 seasons of the Fascinating podcast, the one with the most downloads was the one titled Learning from Fractal Geometry. And since one video is worth many kilowords, I have asked my stable of contributing editors to produce a video with footage demonstrating the fractal objects and processes we are discussing, and I will narrate. All of our contributing editors, except Smirky McSmugface and Betsy Busybody, happily went to work on the job with senior contributing editor Pego Donata overseeing and coordinating the project. Smirky and Betsy demurred, saying that this sends the wrong message, and demurred even further when they said they didn't want to talk about why they thought the message was indeed wrong. What is the message that was emphasized in the podcast? The message was that control is an illusion, and I believe the arguments presented were sound arguments. Naturally, I am more than happy, eager even, to entertain arguments that question the soundness of any arguments I have made, because this is the process by which all of us, Vulcans and Earthlings alike, learn new things and hone our own reasoning skills. They won't admit it, but I suspect that Smirky and Betsy have simply redefined the term wrong. To them, wrong means that it does not support the agenda the two of them are committed to. An agenda which is based on intelligent design thinking, the assumption that outcomes can be chosen and implemented, and that people who think like they do are the ones to do it. Their agenda consists of installing a ruling class with the power to enact legally enforced prohibitions and requirements, and to decide how everyone's money is to be spent, with the ultimate goal of creating a safe and secure future for all. This agenda, of course, assumes the ability to actually control outcomes, and they don't want to hear that the kind of control they propose to rely on is impossible. And they certainly don't want to hear that safety and security are perhaps not the ultimate good. Let's recreate this popular podcast, this time with video enhancement. Let's start with a natural phenomenon that illustrates much, the current of a stream flowing into advancing ocean waves. The stream's current has kinetic energy, and so do the ocean's waves. What happens when these energies tangle? Observe that the tangling triggers an astonishing amount of complexity, both in the ocean's waves and in the river's current. Things happen that might seem counterintuitive until you see them with your own eyes. For instance, the ocean's waves continue to propagate up the river against the river's current for quite some distance. The current and the waves, both singly and together, sculpt the riverbed, including the ground on the sides of the river's channel and the ground on the bottom, in complex patterns. And the sculpted ground in turn influences the flow of the water in a complex interplay. The wave action that continues upstream erodes the sides of the channel, contributing to the river's meandering and the formation of a delta. This is an example of a dynamical process with fractal characteristics that occurs in nature, one of a vast number of such dynamical processes. For much of Earth's recorded history, there have been hints, especially in the world of art, of an understanding of fractals. See, for example, the waves and clouds in the paintings of Katsushika Hokusai, a Japanese artist who lived about 200 years ago and whose work was introduced to Europeans during his lifetime. The Asian concepts of yin and yang also demonstrate a kind of fractal structure. I am told that any manifestation of yang can be further divided into its own yin and yang, and vice versa, and so on ad infinitum. This is an instance of the fractal principle of self-similarity across different scales. Modern thinking about fractals began in the field of weather forecasting. A meteorologist at the Massachusetts Institute of Technology by the name of Edward Norton Lorenz more or less stumbled upon the idea of deterministic chaos and recognized it as significant. In a famous story, Lorenz, who was working on computer-assisted numerical weather forecasting, was running some computer simulations of weather outcomes involving a particular set of variables. At one point, he wanted to repeat a simulation that he had already run, but this time he started it in the middle instead of at the beginning to save time, using as input the data as it was printed out at that point in the original run. To his amazement, he then observed a significant departure in the results produced by the second run compared to the results of the first run. The explanation turned out to be that the data that served as inputs to start the new run had been rounded. The minute variations between the actual numbers and the rounded numbers was enough to send the simulation on a qualitatively different path. Shortly after Lorenz's heyday, the brilliant and intuitive French mathematician Benoit Mandelbrot published The Fractal Geometry of Nature. This treatise, with its rigorous quantitative exposition, opened previously unimagined vistas in science and philosophy. Prior to Mandelbrot's work, mathematical descriptions of the natural world were limited to things that can be thought of as smooth, differentiable in math speak. Think of a sine wave, for example, which has a definable tangent at every point. Mandelbrot showed us that you can also employ mathematical methods to describe things that are rough, that is, things with corners which do not have definable tangents at every point. Think, for example, of the steam rising from your morning cup of coffee. For a certain distance, this steam might rise along a predictable path in what is referred to as a laminar flow. But the path then quickly becomes turbulent as it continues to rise. The resulting pattern is so complex and varied that it becomes impossible to predict. If you can imagine yourself very small and riding on a particular water molecule within the steam, there is no way that you would be able to predict with any confidence where the molecule you are riding on will be in the near future if the flow is turbulent. Traditional methods of mathematics can deal with laminar flows, but not so well with turbulent flows. And although the methods of fractal geometry cannot make precise predictions of future flows, they can reveal useful insights into the evolution of complex systems and the attractors and strange attractors that function within these systems. I am calling attention to fractal geometry because it reveals something quite valuable as we pursue our aim of creating a meaningful worldview based on science and nature. Namely, that any valid worldview must take into account the fundamental unpredictability of natural phenomena. To understand nature's unpredictability, it's enormously helpful to understand fractals at some level. If you are among the few who can deal with the formal mathematics Mandelbrot gave us, good for you. But even without much training in mathematics, you can still gain useful insights into the nature of fractals. You might want to read Mandelbrot's memoir called The Fractalist, which he worked on all his life, and which was published shortly after he died in 2010. His memoir reveals fascinating details about his intellectual journey from childhood on, and about his rare intellectual gifts, particularly his unusual ability to create visualizations of mathematical concepts as a key to deep understanding. In the remainder of this essay, I will describe a few of the basic concepts of this fascinating subject. One key concept, already alluded to above, is self-similarity across scales. An example that helps to illustrate this idea is a coastline where the ocean meets the land. If you look at the coastline from high above, you will see the rough irregularities in the coastline, that is, the inlets and the salients. If you zoom closer, you will see irregularities that you did not notice from higher up. As you continue to zoom, new irregularities will continue to appear, and they look the same. That is, just as rough somehow as the irregularities you see from any other altitude. This phenomenon will continue even if you zoom down to the microscopic level. In fact, you will not be able to tell just by looking at the irregularities in a photograph at what altitude a particular photo was snapped. Here is another example of self-similarity. Two photographs of terrain. One photo taken from an altitude of 30,000 feet and another taken from an altitude of 5 feet. Can you tell which one is which? For a truly dramatic illustration of self-similarity, watch this video clip of Mandelbrot set zoom. The Mandelbrot set is probably his most widely known contribution, and it is generated by a large number of iterations of a relatively simple equation, where the outputs of one iteration are used as inputs for the next iteration. The images look the same, that is, they have the same roughness and the same structures, no matter how far you zoom in or out. Another helpful concept is fractal dimension. You might have encountered a fractal image somewhere or other and noticed that its fractal dimension might be given as, for example, 2.7. What does such a thing mean? At this point, I've actually heard people respond with indignation, conclude that mathematicians are wacko and it's a waste of time trying to understand such an abstract and useless thing as fractal dimension. We all know there are 3 spatial dimensions in the world we live and move in, and apparently 1 temporal one. Common sense tells us that any object exists in some integer number of dimensions. But there's a useful meaning of fractal dimension that is not all that difficult to understand. We will use an object known as the Koch snowflake to illustrate. The construction of the Koch snowflake begins by placing an equilateral triangle in a 2-dimensional space. In the center of each straight line segment, you can then replace the middle third of each of the 3 lines with another outward-pointing equilateral triangle. The first iteration of this algorithm produces a 6-pointed star composed of 12 straight line segments. Transform the object again by applying the same algorithm to each straight line segment all around the new figure. Do this again and again to each newly transformed object as many times as you like. Note that each iteration uses up a little more of the 2-dimensional space in which the object exists, but it never takes up all of the available area, even as the number of iterations becomes very large. And the proportion of the 2-dimensional space it does take up as the number of iterations approaches infinity is its fractal dimension. In the case of the Koch snowflake, the fractal dimension turns out to be about 1.262, and the area of the snowflake converges on a limit of 8/5 of the area of the original triangle. Now let's elaborate on the term strange attractor mentioned above. This is the concept from fractal geometry that most helps us to see why natural phenomena can be so unpredictable. An attractor is any set of points around which the results of a dynamical process may gather. Think, for example, of coyotes and rabbits, or any other predator-prey relationship. If there are a lot of rabbits, coyotes will kill and eat a lot of them, leading to an increase in the number of coyotes. But since there are now aren't as many rabbits left, they will become more difficult for the coyotes to find, and this puts the brakes on the number of coyotes who can survive and reproduce. Fewer coyotes then results in more rabbits, and so on, in a repeating dynamical process. The proportions of rabbits and coyotes will settle in around a set of figures, and this set of figures is an attractor, and in fact a strange attractor. Examples of even simpler attractors would be planets with moons orbiting, or stars with planets orbiting, or galactic centers with stars orbiting. An attractor is a strange attractor if the results of the dynamical process take on a fractal nature. A particularly beautiful graphical example of a strange attractor is the Lorentz attractor. Yes, the same Lorentz who helped launch this scientific revolution. An amazing fact about a strange attractor is that the pathways it produces as a result of the dynamical process driving it never coincide exactly, even though they can be very close together. It also demonstrates again the idea of fractal dimension in that the integer spatial dimension will never be completely filled by the figure being generated. A dynamical process centering upon a strange attractor has the feature of sensitive dependence on initial conditions, sometimes referred to as the butterfly effect. What are the implications of the butterfly effect on the effectiveness of forecasting? Let us say, for example, that you would like to make a forecast of some future state of the economy based on measurements of the values of the variables in the current state of the economy, such as output, employment, investment, etc. We all know, of course, from long-sad experience that economic forecasting is notoriously unreliable. A famous quip is that the only thing economic forecasters have so far accomplished is to make weather forecasting look respectable. The principle of sensitive dependence on initial conditions, the butterfly effect, gives us insight into why it has been, is now, and always will be true that economic forecasting is so intractable, and would still be intractable even if we were to get better and better at modeling the relationships among variables. The problem in a nutshell is that the current value of each economic variable must be measured with infinite precision in order for the forecast to produce results you can trust. If you had an infinite amount of time to make the measurements, you might be able to approach infinite precision, but it should be obvious that you cannot do anything like that in practice. So, if you think that with sufficient political will and good intentions we can collectively control outcomes, you need to think again. As a starting point, you would need a reliable forecast. And it only gets harder after you do that as you attempt to tinker with the variables and guide the dynamics. One more reason to conclude that control is an illusion. The more you think about it, the more wisdom you ought to see in Friedrich Hayek's comment that the curious task of the economist is to explain to people how little they understand about that which they propose to control. Be sure to have a look at the next essay on the fascinating YouTube channel. Please provide feedback if you are so inclined. You may contact me by sending an email to Senior Contributing Editor Prego de Nada, pregodenada@gmail.com. If you find the lessons from nature in these essays personally valuable, please recommend it to your friends and give it a like. Thanks to Truck Tribe for permitting the use of their song Helium. Live long and prosper. Savor your experiences and treasure your memories, and respect nature's wisdom.